SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. In the last class, we were talking about the method of weighted residuals, and then we were looking at how it can be changed to a weak formulation. The weak formulation has some implications and some advantages, and then we are trying to explore what are the important points. So just to recall, so what we said is that this is the weighted residual form of the original statement, in the sense that as given in the differential equation itself. This is how it is given. L5 plus F is equal to 0. And then we pre-multiply with Wi. And then this is a weighted residual statement. And here, of course, when you make the approximation for phi hat, so we should make sure that this doesn't go to 0 identically, or it is not multiply defined, in the sense that it's a continuous. L phi hat has to be continuous and well-defined function so that the integration can be performed. And so now what we would like to do is that, is it possible to reduce the differential order of L? So that is possible by doing a partial integration of that, in the sense that if you do the partial integration, so then what we do is that, so this becomes Wi, a boundary integral, and then this is an operator, and again a differential operator, then followed by a domain integral with a part of the differentiation going on to Wi, and then this L is changing to another differential operator B. So what you need to observe is that all the C, A, B are all differential operators. So one thing that is need to be observed is that particularly B operating on phi hat, which is the approximation, is of lower order compared to L. So obviously, if when we say that this integration should be capable of doing this term L phi hat, so the same thing if you do it here, this integration on omega, so this also should be well defined. B phi hat should be well defined. So by comparing these two, so what we can say is that since B is of lower order compared to L, so the requirement of differentiation on phi hat is reduced in the case of this form. Okay, so that is why though both are same, so this is called the weak form of the method of weighted residuals, because the continuity requirement on phi hat is reduced. I hope just to recall what we mean by the continuity requirement. For example, we can just look at one dimension representation phi hat. So let us say that at x is equal to, so it is defined in different manner. So what we can say here is that just to give you an insight into what we mean by the continuity. In fact, this is what we are going to use later. So if the function is defined piecewise, let us say, it is defined by one function here before x is equal to a and by another function slightly. So in this case, you can see that this seems to be a quadratic here and a quadratic here. But the only thing is that it's defined by different quadratics. So if you take a first derivative, so then it looks like this one. So the derivative, but however, it is changing the kind of slope here and it looks like that. And if you take a second derivative, then it looks like this one. So this kind of function is called the first derivative is existing for this one, but not the second derivative. Second derivative has a discontinuity. So this kind of function is called C1 continuous function. Okay. So if you have what kind of order, if you have L as a second derivative, then what we need there is a second derivative should be existing, a well-defined function. So that means that this kind of continuity, as such, this kind of continuity is not enough. So for that, we really require d square also to be continuous. So that means that we require here, if you have a d square occurring here as such at this moment. So if you have a d square occurring in L, so then what we require here is that d square here has a discontinuity. So this is not acceptable. And what is that we require? We require a C2 continuous function, right? But if you come to this weak formulation, so B will become the B will become a lower order d dx. If it is only first derivative, then you can see here very clearly that this kind of approximation has the first derivative well defined, and this is acceptable to us. So that means that here, if you go for the weak form, so this you can use a C1 continuous function. So this is the important observation, that by doing this partial integration or the weak form, so then this weak formulation will admit a lower order continuous functions. So in fact, we are going to have one more advantage, which I am going to show right now. But at this moment, as I was telling in the last class, is that, so if you get the solution here for phi hat, and if you get the solution for phi hat here, are we getting the same thing, or are they going to be different? Because if we are going to work here, so are we going to get a different solution? So the thing is that this phi hat, so since you have only the continuity requirement of lower order, so you have a bigger class of approximations that are admitted, so which will contain this also. The thing is that in most of the practical engineering applications, so most of them are linear operators of this kind, and the solutions are unique. So if you have a solution, and then if this contains that solution also, obviously this also will give the same solution. So only thing is that we are looking at a larger class of functions using this formulation. Okay, so we will have more freedom. That is one advantage. And then now let's look at another advantage. Is so what we have going back. So looking at the another advantage. So the problem is defined as L phi plus F is equal to 0 in the domain omega, and M phi plus C is equal to 0. So one of the requirements we said that on phi hat is that you should satisfy this boundary condition fully on the boundary, and then we are looking at this one. So what we are looking at is so this is the weighted residual statement, and then this is what we said we are actually doing. But then the precondition for this one is that phi hat should already satisfy the boundary condition, and then we are trying to get what is the best function phi hat which satisfies this weighted statement. Okay. So, but the very fact that we have this need to be satisfied is sometimes is not easy. In fact, if you recall heat conduction problems, if you recall some of the heat conduction problems here, so one simple boundary condition is defining the temperature phi is equal to phi bar on some part of the boundary, and in the some other part of the boundary which we call as flux boundary condition. So here we say that here the flux is given as Q bar. So here the boundary condition on this one, on gamma phi, is minus K dou phi by dou N should be equal to Q bar. So this is the heat leaving the body is given as Q bar, and that should be equated to the derivative of phi itself. The N is what? N is the unit normal perpendicular to the body. So this is how this condition. So one of the things here, phi is equal to phi bar on gamma phi, is not difficult to satisfy, but however this kind of derivative boundary conditions, okay, Newman boundary condition which they call it, is a little difficult to satisfy. So for that, what we would like to do in this formulation is that we would like to, so we will not be satisfying this equation boundary condition, but however we are going to add, so in this, so let phi bar not satisfy the boundary condition, then what happens is that then the residue on gamma, for example here gamma Q, is added into weighted residual statement. So this is the residual statement, and then what we are saying is that, so we are not going to satisfy this boundary condition a priori, and then we are going to add, because if it's not going to satisfy, obviously it is going to result in error or result in a residue which should be taken care, and that also will be added into this. So what we mean by that is that this is the original L phi F, so which we're doing, and then to this we are going to add another weighted term M phi hat here, but then this is an integral on the boundary. So this is the residual term in the domain omega. That's the basic governing equation, and this is the term again, because it's not satisfied as a priority, so prior to starting this work, so we are going to have this one together with another weighting function wi. So this wi, we call it as a prime. So this may be different from this one, or it may be related in some way. So we are going to see that soon. So what we have here is that if you look at this one, we already have seen the weak form of this one. So we said that it is doing partial integration. We did this, and then there we said that this is going to result in a boundary term, and followed by this one. Of course, we have this. So this is this is a weak form which we just saw it earlier, and so this is the bounded term, and this here b is of a lower order, and this is on omega, and then we also have f here, so that continues to be here, and this together with the weighted residual on the boundary. So okay, so let's look at this one. So what we have done is that this is the weak form of the original statement, and then this is the weighted residual statement on the boundary of the boundary condition. Okay, and interestingly, so there are possibility of this boundary term here. There is a boundary term here, and then there is a boundary term here. So one thing is that these two may be cancelled, and it is in fact so. That's because here this is C is of a lower order, and the boundary condition here, that M also is of lower order, so maybe they are of a similar nature, and by somehow suitably taking this Wi prime in relation to Wi, maybe it is possible to cancel. Okay, and of course this is not difficult, Wi prime G d gamma, so that can be integrated. So what we have done here is, okay, we are smart and intelligently we are able to manipulate that in some way, this Wi prime, so that it gets cancelled with this one, and then this whole thing can be neglected. So that is another very big advantage of this weak formulation. So the difficult boundary conditions may be cancelled. The other, why I say difficult boundary condition, so this is the something like this one, which is the derivative boundary condition. So that is difficult to satisfy as a precondition, right? And of course, phi is equal to phi bar can be satisfied only this on gamma, and this is, I'm sorry, on gamma q. Gamma q. Gamma is not phi. This is gamma phi. This is gamma q. I'm sorry. A small modification, please. Okay. So this is the advantage. This is the second advantage. The first advantage is that the derivative requirement on phi has been reduced. The second advantage is that by taking the residual of the boundary condition, then it is possible that it may be cancelled. So we are going to see this problem in relation to the heat condition problem. But before embarking on that, maybe we'll take an example of one-dimensional analysis of a rod which is subjected to axial load. and we are trying to find out what is the axial deformation. So I'll revisit this one. In fact, this is very important for us, and I will go into see how this can be cancelled. So I'll come back to that. So before that, I will just try to see how these things can be implemented in relation to one-dimensional problem. So let us take one-dimensional example. So we are going to illustrate this weak form by taking the boundary condition into the weighted residual statement. So we'll just take 1D example. Of rod subjected to axial forces. So obviously our interest to find out this is something similar to which we are doing. So this we have derived. So the deformation, the governing differential equation is d dx of AE du by dx plus Q is equal to 0 in 0 to L. Okay. This is where U is the axial deformation. U is equal to Ux. One variable problem only, axial. Axial deformation. And A is the cross-sectional area, maybe function of X. E is Young's modulus. And what is Q here? Q is here. Q is distributed force on the rod. Okay, so this is how we define the problem. And of course, the boundary conditions are in this particular case. So the at x is equal to 0, we have it's rigidly connected, so it's u is equal to 0. And at x is equal to L, what it is? So a load P is applied here. In addition to Q, we also have the load P applied here. So here then is nothing but AE du by dx is equal to P. So everything is evaluated at x is equal to L. So this is, well, so okay. So the whole thing is, so that means that du by dx is the strain multiplied by E, that is the stress, and multiplied by A. So that will give you the overall force on the complete cross section. So which should be equal to the another applied load P, which is the boundary condition. So these are the two boundary conditions. And let us see how we can weighted residual statement, which includes the boundary condition also. So let's look at is that, so what we have here is that Wi d dx of AE du by dx right? Multiplied by Wi. So this is 0 to L. So this is the residual as far as this main governing equation is concerned. And then to this, we add not both, we add the term at the right end. The left end x is equal to 0, u prime is equal to 0. So this is not very difficult to find. But however, the derivative here, which is being found out at x is equal to L, so that's a little difficult one. Okay, it's not impossible, at least for 1D it can be done. But what we do here is we are illustrating the weak formulation together with the boundary condition. So what we do here is that, so Wi prime multiplied by AU du by dx, maybe I can put prime minus P evaluated at x is equal to L. Okay, so this is the boundary condition, AE du by dx. I take the P on the other side, so this is the residual, right? And multiplied by Wi prime, and the whole thing is evaluated at x is equal to L. So this is not really an integral over gamma. So this is just because the boundary is just a point. Boundary is not really a curve, boundary is just a point. So this whole thing should be equal to 0. So the whole thing, this added to this one, should be equal to 0. So this is the residual statement. So let us do the integration one by one. Is Wi, the first term, and we do the partial integration. So doing integration. So what we have here is Wi AE du hat by dx evaluated at x is equal to 0 and L. So this is the boundary term minus dwi by dx times AE du hat by dx, and we also have the other term wi q dx. Okay, so this is the boundary term because we did the partial integration here. So it is Wi, this is gone, and AE du by dx at x equal to 0 and L. And then this comes dw by dx, AE du by dx plus Wi times q is equal to 0. So this we also have to add Wi prime AE du by dx minus P. So this is the boundary condition at x is equal to L. So this is the weighted statement, and so there seems to be a lot of statements, but let us see. In fact, this first one here, can I write it as two terms? So here, the first term, this is at x is equal to 0 and L, which can be written as at L minus at x is equal to 0. So expanding this one, what we get here is that Wi du by ds at x is equal to L minus Wi AE du by dx at x is equal to 0, right? And the other terms will follow, just the same thing. Okay, and so these are the terms. So we will continue. So this is evaluated at x is equal to L. Okay, so these are so many terms are there, and we have to look at each one of the terms and see how we can simplify this equation further. So let us stop at this moment, and then we'll continue this discussion in our next class.